I'm going to be talking about the secant and cosecant function graphs. Let me start by drawing a picture of the secant function graph. Okay, so there's a picture of the secant function graph. Notice a few things about the graph. Notice that the two valleys are separated by a distance in the x direction of 2 pi, and the two peaks are separated in the x direction by a distance of 2 pi. So we can therefore say that the period is 2 pi. I'll write it as a capital T, which is commonly used to denote the period. The possible y values, the set of possible y values is unbounded. The range is unbounded, so we can't define an amplitude. Okay, the domain includes values far to the left and far to the right, except for the locations of vertical asymptotes. All right, so the allowed x values, therefore, are everything except for values where x does not equal plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, so on and so forth. Okay? Everything else is allowed. Now, notice regarding the y values, notice that we have all y values greater than or equal to 1 and all y values less than or equal to 1. So a compact way to denote that is that the range includes all y values such that the absolute value of y is greater than or equal to 1. Okay? Now let's study the cosecant function graph. So give me a minute to draw that. All right, so there is a sketch of the cosecant function graph. And notice that the distance between the peaks in the x direction, with respect to the x direction, is, again, 2 pi. And the distance between the valleys is also 2 pi. So we can say that the period of the cosecant function is 2 pi. Now, the graph, the y values with respect to the cosecant function graph extend as high up as you care to look. In other words, the range of the cosecant function is unbounded, okay, in the positive and in the negative direction. So we can't define an amplitude. Once again, we have vertical asymptotes, so the domain includes all but the values associated with the vertical asymptotes, so all except for 0, plus or minus pi, plus or minus 2 pi, and so on and so forth. The range, because the y values include everything greater than or equal to 1 and less than or equal to negative 1, the range is, can be compactly stated as all y values such that the absolute value of y is greater than or equal to 1. Okay? Now, if you look carefully at the secant and cosecant function graphs, you'll notice that they look like one can be, any one of them can be interpreted as the other one with respect to a horizontal shift. So if you do a horizontal shift, the correct horizontal shift on either the secant or the cosecant, you can turn it into the other function. Okay? So thinking along those lines, you can see that the cosecant of x must be the secant of x minus pi over 2. Okay? Remember that subtracting pi over 2 from x is equivalent to shifting the secant graph by pi over 2 in the positive x direction. And if you do that, the secant graph will be, all the points will be resting right on top of the corresponding points on the cosecant graph. Okay? Now, let's talk about transformations with respect to these functions. All right, so what would the graph of 10 secant of x look like? And also, what would the period look like? Okay? So, the effect of the 10 is going to be as if the original secant graph was stretched vertically. Okay? So that will look something like this. Okay, so it essentially looks like the original secant graph, except that the valley is not at the y, the y-intercept is not at the y equal 1 position, but now it's at the y equal to 10. Okay? So that affects the y-intercept. It stretches it vertically, but it has no effect on the period. Okay, the period has to do with the distance between the peaks and the valleys with respect to the x direction. So the period is still 2 pi. Okay? Now, what about the graph and period of the secant of 10x? Okay, so how is the period going to be affected by the 10 in that position? Let me show you what the graph would look like. Okay, so the y-intercept is the same as for the original secant graph, so we haven't stretched it vertically. The effect of the 10 in that position is to change the period. It's when you multiply the x by a number, it's like either stretching it or compressing it horizontally. Okay, and so notice that for this function, the graph has a period of pi over 5. Okay, now just like we noticed, you may have noticed previously for the cosine graph, if you study lots of graphs with different coefficients in front of the x, like secant of 2x, secant of 3x, you'll notice this pattern that for the secant of kx, the period is 2 pi divided by k. All right? So for this, it would be, of course, 2 pi divided by 10, following the pattern, which reduces to pi over 5. All right, now let's see how the next transformation affects the plot. What about 10 plus the secant of x? So give me a moment to make a sketch of the graph. All right, so almost done. So there is a sketch of the graph of 10 plus the secant of x. So the effect of adding 10 is to raise the regular secant graph vertically up by 10. And so the period is not affected. So the period is the same period as for the regular secant graph, which is 2 pi. Okay, and again we have no amplitude, so that's that. All right. Now I would like you to sketch a graph and determine the period of the related function. So would you please graph 1/9, sketch the graph corresponding to the function 1/9 times the cosecant of x, and also determine the period if you can. Okay, so pause the video and do that now, please. Okay, so I'll go ahead and do that. So the effect of the 1/9 is to compress the graph vertically. So it'll look something like this. Okay, now the reason that the graphs look so flattened again is because of the 1/9. So that does not affect the period. So the period of this graph is 2 pi. Okay. Now, would you please try the following? Can you graph the, can you sketch the graph corresponding to the function, the cosecant of 9x, and find the period of that one, please? Okay, so pause the video and do that now if you like. Okay, so I'll go ahead and make a sketch. All right, so there's a sketch of the cosecant of 9x, and the effect of the coefficient 9 is to compress the graph horizontally, and so that will have the effect, it does have the effect of making the period change to 2 pi over 9. All right, so just like with respect to the secant function, if you graph the cosecant of 2x, 4x, 6x, etc., you would notice the pattern that the cosecant of kx has a period of 2 pi over k. Okay? Now, for the last one, what about 5 plus the cosecant of x? So again, pause the video and try to determine the graph and the period. All right, I'll go ahead and do that. All right, so there's a graph of 5 plus, the graph that corresponds to the function 5 plus the cosecant of x. I can draw one more piece if you like. Maybe even another one. So the effect of adding 5 is to shift the regular cosecant graph up by 5. That does not affect the period, so the period is 2 pi for this exercise.